Okay, so the next topic is traverse closure and adjustments. So again, I'm not sure how much they will tend to go over this or have on your test, but we're going to look at types of traverses very quickly, look at traverse closure, traverse adjustment, ultimately then getting that into coordinates, and the last thing we'll take a look at are side shots, which is a typically pretty easy process to do. All right, so the first thing, just understand that a traverse is just a series of consecutive lines that you measure your lengths and you measure your angles. Okay, so those have been determined. You kind of have two primary types of traverses, open and closed. We would never use an open traverse, so we're not even going to consider that. So the closed traverse, that comes in two categories, a closed polygon or what they call a linked traverse. So you could probably be hit with either or, but the polygon is the more traditional, where you're starting at a point and coming back to that same point. In the linked traverse, you're starting at two known points. One is the point you're occupying, and the other one is your backsiding, which we call an azimuth mark. And you're ending at a secondary point and azimuth mark. And those 4 points have good control information on them, so they have northing and easting and all of that. So that would be your link. They're essentially the same type of traverse and how they work. So what we have is, when we do this, traverse provides, of course, a check in angle and a check in distance, and of course it's used extensively for control if you're doing a ground or a terrestrial-based type of work. So the open traverse doesn't connect to anything. There's no means of check. It shouldn't be used. In my opinion, it should be used for anything. All right, so traverse calculations, if you're doing either the linked type or the closed type, which we're going to look at a closed type of traverse, goes through several steps. First thing you're going to do is check your angles, balance them. Then if they don't fail your first test, if they're not out of whack, like if you're not busted by 2 degrees, you're going to balance them. And then you're going to calculate directions around your lines, and either in terms of azimuths or bearing. Azimuth is easier to do because, again, your sine and your cosine values are coming in based on the calculator providing the negative and positive. If you're using bearings, you're going to have to apply those signs. Then we would calculate latitude and departure for each course. And from that, then we'll be able to get what's called an error in latitude and an error in departure. And that'll determine how much we're not closing. Then that'll allow us to calculate linear misclosure and relative precision. And ultimately, if we pass the relative precision test, we would adjust the traverse. And once the traverse is adjusted, we would calculate coordinates. So traverse calculations, when we look at balancing angles, typically what we're saying is we're going to determine the angular misclosure. So basically we take the interior angles and we sum them up, and we take a theoretical summation and we subtract that. So theoretical sum, for those of you guys that don't remember, it would be n minus 2 times 180, where n is the number of sides or the number of angles, and that'll tell you what you should actually have. So for instance, a 3-sided traverse, 3 minus 2 times 180 gives us 180 sum. So that's how you're comparing them. Then typically you just distribute that. Most people would use what's called an equal distribution. So you just take your misclosure divided by your number of angles and you distribute that. I would imagine if they give you a test question like this on this test, it's going to probably be an equal distribution. So you should be looking for a number that's going to divide equally. Okay, so if you come up with 13.2, you're probably not doing something right as your amount of distribution, because I don't imagine that they would give you something that involved. Okay. So the next step, of course, is calculating azimuths or bearings. You're going to use your balanced angles to do this. So if you use the original given angles, it's not going to balance. Your traverse isn't going to close in terms of azimuth or bearing. So make sure that you're using your balanced angles. They're going to give you, or you're going to have an initial direction that's given, either an actual one or an assumed one. Of course, on a test, they're going to give you one. So you're going to have to use that. So traverse calculations, after we get to that point, we're going to calculate latitude and departure. Latitude and departure we've already looked at in terms of the inversing on direct routine, so it's the same process. Latitude is going to be your distance of your course times the direction of that course. Departure is distance times the sine. Now, again, bearing can be expressed in azimuth or bearing. or theta can be expressed azimuth or bearing, it's really advantageous to use azimuth because you don't have to worry about signs. Your calculator provides that. So if you are using bearings, then you're going to have to determine algebraic signs. So again, this little chart we just looked at before, northeast is plus plus, southeast is negative plus, southwest negative negative, and northwest plus negative. All right, so when we get into misclosures, what we would do is we would take our column of our latitudes and just sum it, and that'll give us what's referred to as error in latitudes. And you're going to get a magnitude of that, and you're going to get a sign of that, and both of which are important. Departure then would be the summation of the departure column. And again, you're going to get an error in departures, again a sign, and a magnitude. And for a linear misclosure then, we simply take the Pythagorean theorem of that. So we would take the error in latitude squared plus the error in departure squared, square root. That's going to yield my linear misclosure. The angle, if you need it, can be determined by departure over latitude. Most people don't care about that. Okay, so that's less important. But the linear misclosure, the distance component of that, is the real important thing, because we're going to use that in the next step where we're going to talk about relative precision. Relative precision is defined technically as your error enclosure or your linear misclosure divided by the perimeter of your traverse. But ultimately, when you do that, you just take the reciprocal, because we're looking at that's being 1 in something. So if we had a 0.52 misclosure, linear misclosure, and we're 8,520 feet, and we divide that, you notice we get this very small number. But if we take the reciprocal of that, we will get 16,385. So we would express that as a 1 in 16,385 precision. So then there's different types of adjustments. Really only one of them is doable by hand, and so the only thing I would imagine they would ever reference you by hand is the compass rule. Transit rule was the older style rule. You probably can't even find that in most surveying books anymore, but that was assuming that your angles were better than your distances. And so then when you did this adjustment, it threw most of your adjustment into the distance and less into the angle. Compass rule is across the board. It assumes that angles and distances are about the same quality, so it's going to just kind of generalize do it, and it's very easy. Both Crandall's methods and least squares would be very difficult to do by hand, and I can't assume that they would ever show you that on a test. So we're just going to consider the compass rule. So the compass rule basically works in 2 steps. You first calculate a correction for each latitude and departure, and then you apply that correction to adjust it. So basically, your correction for latitudes is the error in latitudes divided by the perimeter times the distance of the course that you want to correct. So if you have 5 courses, you're going to have 5 corrections. You're not going to have just 1. Also notice there's a negative sign out front, and what that's doing is just flipping the sign of your corrections. So if your error in latitudes are negative, all your corrections should be positive. That's all that's really saying. Departures work the same way. We take the error in departure, divide it by perimeter. We multiply it times the distance, that constant times the distance of the line we want to correct. 5 sides, 5 departure corrections. And then once you have your corrections, then you can apply them to your adjusted lats and your departures algebraically. Now you have to make sure that you add them algebraically. So if you have a negative latitude and a positive correction, then it's getting less negative, okay, kind of thing. So you have to make sure, and at the end, you can just simply sum your adjusted latitudes and your adjusted departures, and if you've done it properly, it's going to go to 0 in both cases. So that's how you can check that. Okay. And then traverse calculations, what you do is you have a given value typically that you're starting with, and you're just going to work it around the line. So if we started at A, we would go from A to B, and then we go to B. So notice at A we're using the latitude A to B to solve for B. Then when we get to B, we're going to use the latitude B to C to the next point, and you just go on and on and on. When you get done, if you come back to A, you should end up with the coordinate you started with, and the departures work the same way. Okay? So whether you're working in X's and Y's or northings and eastings, again, I would say on this test they could hit you with both. And they just might just to kind of screw you up, so just keep in mind what's going on there. So those are your calculations. So we're going to take a look at a simple example here. So this is This is a traverse we're going to look at now. We're starting at a point 1 there. It's given 5,000, 5,000. We're traveling from 1 to 2, 2 to 3, 3 to 3 back to 1. What you're noticing, I have already calculated angles on this. We'll take a look at the problem here more specifically, but this is showing you bearings that have been calculated for you based on the raw angles actually, I believe. And then those distances would have been measured distances in the field. So here we have our little traverse that we're looking at. Now what this is referencing or representing, starting at 5,000, 1, 2 to 3, we've measured interior angles, the angle at 1, angle at 2, angle at 3. So those are unadjusted at this point. Those are just raw angles. And then we have the raw distances that are given. And this is our starting direction. So the first thing I'm going to do is do my little calculation and determine what kind of misclosure I have in my angles. So I take my angles and I sum them, 1, 2, and 3. Notice that I come up with a 30-second bust. And it's over. Well, I know that because, again, n minus 2 times 180 tells me that this should be 180. So in this case, very simply, divides by 3. I'm going to subtract 10 seconds on each. Now, make sure you go the right direction because it's real easy to add 10 seconds, and then of course when you sum this up at the end, it's doubling the error. So we would not want to see that happen. Okay, so from that, from these raw angles, we've adjusted the angles, and then what we're going to do is take the initial starting direction, not using this angle, we're going to use the adjusted angle to come up with the adjusted bearing. So this would be the adjusted bearing, 2 to 3. And then this would be the adjusted bearing 3 to 1, utilizing, again, the adjusted angles. And the last thing you would do is use this adjusted angle to recalculate this. If you don't come up with that starting, then you're not using it. You're not either doing it right or you're not adjusting it right. So then we kind of go into a tabular form. I'm sure you guys, most of you guys have seen this before. So this is what you might call a traverse closure type of sheet, wherein I'm going to have a line column, a bearing or azimuth, depending on what I'm using, distance, latitude, and departure. So I just write the information down. I've got my bearings, 1 to 2, 2 to 3, 3 to 1. My distances, okay. One thing, of course, if you're doing this, be careful. Transposition's real easy. If I've got this is 287.60 and I write 0.6, obviously that's going to create a huge mistake for me. So in the real world or on a test, we got to be careful with that. We're going to need perimeter, so I just go ahead and sum that right away. There's your perimeter. Okay. So then we're going to take latitude and departure. So again, cosine of that times that gives me this. Sine of that times this gives me this. But remember, the northing, eastings, if I'm using bearings, my calculator is giving me pluses across the board. So I'm looking at this. I've got south. Here's what I do before I even calculate anything. South, north, north is negative, positive, positive. I'll go ahead and write these before I do any calculation. Same thing here. West, east, west, negative, positive, negative, negative, positive, negative. Then I've already taken care of that. So once I have calculated all of those, I just sum them algebraically, and this is giving me 0.23 of a foot positive. So I'm out in a northern direction, and this is in a western direction. Okay, so that's my air and latitudes. This is my air and departures. From that, we're going to get my linear misclosure. Linear misclosure is simply your latitude air squared plus your departure air squared square root. So we get a value of 0.33. So that's our total amount of air. And when we take the precision of that, we take the precision, the air and latitude, the air enclosure divided by the perimeter, and we come up with a 1 in 2,921. And I hope no one does work of this quality because you're not doing quality at all at that point. So, all right, so that would be the next step then. If we're going to adjust this, which we actually wouldn't, we're going to calculate our corrections here. Okay. Oh, did you? Here. Let's go back to this correction.
Oh, okay.
So down below, notice what we've done. This is my corrections for latitude, corrections for departure. So we're taking the air and latitudes from here, dividing it by the perimeter, and multiplying it times the distance for this one. So the air and latitude divided by the perimeter times this distance gives me this number here. But notice I'm not getting a negative, but what we're saying is these are all positive, so we have to correct them negative. Okay? So all we're doing is flipping the sign. So we're going to do that for each course respectively. Now notice what I did is I had to do a manual correction because if I sum these guys up, it should come to 23, and when I did it initially, it would have been 24, so I would have still had a 1/100th of a foot bust. So we can just do something like that. For departure, you're going to take your error in departures divided by perimeter times the distance of the line that you want to correct, and you notice that's what we're getting here. And these worked out really nicely. Again, sign is opposite. Okay, so now we're going to add these respectively to these. So to get the adjustants, we're adding those, and what we're coming up with then is the adjustants. So we're adding the correction to the raw latitude, gives me this, correction to the raw latitude, correction to the raw latitude. When we sum this column, it should go to 0. If it doesn't, you've done something wrong. Same thing with the departure corrections. You add those corrections to the raw departure algebraically. Again, if that's done correctly, that should sum to 0. So the last step on this is to calculate then the coordinates. Notice we have a starting coordinate starting at 5,000 northing and 5,000 easting. That was given. So very simply in this chart, all you do is you just take the 5,000 plus this algebraically and you write it right here. Okay, so very simple. 5,000 plus the negative 232.60, it gives me this. Then we're going to take this value plus the 70.58, add them, and that gets written here. And ultimately we're coming back to 1, so we're taking those and adding them, and this should come back to 5,000. If this is 0, this has to come back to 5,000. So if it doesn't, you made a math mistake. That's just a really simple check. We do the same thing with the eastings. Eastings in this case plus the departure gives me that. You can just see kind of how you're doing that, and it just works that way all the way through. Okay? So there's your traverse adjustment, closure, and coordinate calculations. So typically the next thing you're going to do on a traverse, once you've resolved it and you've got your good points on all your controlled values, you're going to side shot. And side shot are things that are external. So this is representing my little traverse that we just did, and these are the adjusted coordinates. I'm not seeing point 1 up here, but we would typically have that in a full view. So what you've done also, while you're out in the field, you've got something to locate, in this case point 50. I want to get a coordinate on that, but it wasn't in the original traverse, so I'm going to side shot it. So what I do is I turn an angle off of one of the lines on my traverse, and I measure a distance. And by knowing the angle and the distance, I can determine that coordinate value. So this is what we call a side shot. Now we can't really adjust these, so these are going to come through the work of the adjustment of what we've done here. So what you're going to do is very simply do an inverse and a direct routine. So we're going to inverse. In this case, I'm inversing the line 2 to 3. That would give me the direction on the line. If I know that direction and I know that angle, I can solve this direction. And once I know that direction and that distance, I can calculate departure and latitude, and then I can add it. So basically it's an inverse routine and a direct routine. So side shots, I kind of break it down into 4 steps. Solve my backside direction first through an inverse, then I solve my foresight direction, then I solve my foresight latitude and departure, and then I solve my coordinates. So what we're looking at is we have coordinate 2 and 3 given. We're occupying 2, backsiding 3, so we're doing an inverse. So notice there's my latitude and departure inverse, my bearing, and what I'm coming up with is the bearing on the direction of that line of north 79, 49, 37 east. So knowing that and this angle, it allows me to solve this. Now notice what I've done here is I put it in terms of azimuth, because azimuth is nice because it just makes it simpler when I do my math. So latitude again is distance times cosine, and departure is distance times sine. Now notice I've plugged in my azimuth here, and the beauty of that is that it gives me the negatives and the positives without me having to deal with that in terms of a bearing. So I could do it either way, it really doesn't matter. But this would be the direction of the foresight, and this is the latitude and the departure of the foresight. And then we just apply those to the coordinates that we're coming from. At point 2, so notice we're northing 50 is going to be the northing of 2 plus the latitude 2 to 50. We add those algebraically. We get that coordinate value, and the easting is our easting at 2 plus our departure 2 to 50, and that gives me that value. 910.18 feet. So basically we had 110 feet of vertical change, which if you're doing that with a bench tradition, the differential leveling might take you a while to achieve. The beauty is that we get a pretty good number here, but just keep in mind it's not going to be as good because you have potential source of error here, potential source of error here, potential source of here, and you also have refraction and those kind of things happening. So after we've gone through what we did on the other picture showing, this was the DMV column, and notice I always check that, make sure that's good. I calculated my double areas, so I'm going to sum these algebraically. Gets me that number here. Again, you remember you have to divide that by 2 because that's your actual answer. And so if you converted that to acres, we would have 5.672 acres.